Okay, it looks like it's about 9:30. So let's take a minute and looking at this energy diagram, please label all the information you think you can on this one. And to remind you, I'll write a few things down here. There are the things that you should be able to label. Okay, let's take a look. All right, so reactants, that's where we're starting over here. The products is where we end up. At the top up here, these are our transition states. And in this case, we have two. That's a transition from one species to another. This in here is the intermediate. If we look at the distance between our reactants to the top of our transition state, this is our energy of activation. We also have another one over here, a smaller energy of activation. And then if we look at the difference between the energy of our reactants and our products, that gives us our delta G. And in this case, we see that delta G is negative. Okay, so you should be able to do this type of problem. Any questions about this one? Okay, we ended up on nucleophiles and electrophiles, so let's start there. Okay, and what we're looking for electrophiles is electron rich and available electron density. And the electrophile are electron poor. Okay, and can accept electron density. That one's going to be important for a couple of species where they look like they should be electrophiles, but they can't actually accept any electron density. So the best way to do this is just look at a few examples. So let's take a look at so in these three, let's first look and see what we have. So this is where going back a few chapters is going to help. So if we have a bromine, we know that we have an electronic dipole. So we have a dipole moment going towards the bromine. So that means we have a partial negative and a partial positive. The bromine does have lone pairs, but we also know that halides like to form how many bonds? Well, they form one bond, right? And they tend not to be positive, right? So when we look at this species, right, if we're going to label this, that carbon right there is electrophilic. And we could think about possible reactions of that, but just looking at nucleophiles and electrophiles, that carbocation is electrophilic. The bromine has lone pairs, but since it only forms one bond and it doesn't form positive species very readily, you could do it at really high temperatures, but very readily, not like oxygen, which will form a positive oxygen. It's not like it wants to do it, but it doesn't mind doing it. And so we really don't see that as being nucleophilic. Looking at the second species now, we don't really see any inductive effects, but what we have to remember is that this pi bond is actually made of these p orbitals coming in and out of the ring, right? So we have that pi bond is actually showing that. This electron density, right, is available, right? The pi bond is a second bond is weaker than a sigma bond. So a pi bond is weaker than a sigma. So therefore, this is available electron density, which means that this pi bond, this double bond, is a nucleophile. In the last species here, we have a full negative charge. Anytime you have a negative or a positive, it should key you in. So here, that negative, right, is going to be my nucleophile. Now, I do have a dipole moment going towards the carbon here, but that carbon is not likely to accept electron density. And that's because of the oxygen negative next to it. So in this case, this is nucleophilic, and that's about what we have. Let's look at a few more and you can work these with me. In this species, this first one down here, we have a dipole moment here. We've got a lone pair there. So that means this is going to be partially positive. This is partially negative. The bromine does have lone pairs, but they are not really available, right? So therefore, we know that that position is electrophilic. And then the lone pair over here makes this a nucleophilic position. So in this species, we have a nucleophile at the nitrogen. Those lone pairs there, I could add, give those away and form the nitrogen positive. That doesn't form a fully unstable species like it would if I tried to add something to the halide. So therefore I get electrophile and a nucleophile. If we would look at the next one, we've got, again, we've got a dipole moment here plus a weak pi bond, right? So we get partial negative, partial positive. And in this species, in the same general area in this carbonyl, I have an electrophilic position at the carbon of the carbonyl, plus I have a nucleophilic position. The lone pair on the oxygen could go pick up a proton or react with something. So in this species, really in the same carbonyl area, I have two different. So how this reacts depends on what I bring to react with it. If I bring a strong nucleophile, it's going to react at electrophilic position. If I bring a strong electrophile, it'll react at the nucleophilic position. Okay. Questions about the nucleophiles and electrophiles? Now notice that the carbonyl also has a lone pair, has a pi bond. The pi bond could be considered nucleophilic, but here the lone pair is going to be your primary nucleophile. The pi bond would be a secondary nucleophile. And in most cases, you're going to react at the pi bond, at the p orbital, you're going to react at the lone pair first, right? Just as if you had a negative charge, you're going to react at the negative charge more than you are the other species. Okay.
Hi, I have a question really quick.
Mm-hmm.
Would you say that a lone pair is kind of a representative of a nucleophile being there?
It is, depending on what the element is. So in the halides, that lone pair, so if we think about, let's say we took, let's pick a better fairly color. So let's say we took methyl bromide, right? And I bring another, electrophile. I bring a strong electrophile there, right? So this carbocation would be a strong electrophile. If we look and see if this lone pair reacted, right? So I'm giving my electrons to that, what I end up with is this species. With the positive on the halide, right? This is very unstable. So although that lone pair there is likely to react with it, it's not really available. The bromine doesn't like to be positive, right? So this reaction would quickly decay back to the original. So in this case, we probably we wouldn't identify halides as nucleophiles. We'll see in a second that we will identify halides in this species as leaving groups, which we haven't got to yet. That's the next section. But we wouldn't identify them as nucleophiles because the product of that lone pair reacting gives us a very unstable species, which is not going to be consistent. But if we look at other lone pairs of other elements, so if we look at water, here the lone pair, let's say we just react it with H+. Here the lone pair is the nucleophilic agent, right? It's the nucleophilic position. The oxygen is the nucleophile, but it's the lone pair that's actually being donated. And I get this species, and this is something that we have and we can think about having under normal conditions, right? This is what you have in vinegar, right? So that's not anything that we consider incredibly unstable. So in this case, the oxygen is there, and then even more so if we go to nitrogen, like ammonia reacting with acid, right? We can think about this as acid base, but we can also think about it as nucleophile electrophile. And well, let's we've already used an acid example. Sorry, make you redraw this, but let's use a nucleophile example with a carbocation. And so here, the lone pair can react as our nucleophile. Okay. So lone pairs are nucleophilic, but in halides, we tend not to label those as nucleophiles because they don't actually proceed to reaction. So the availability of that electron density in a halide is limited.
Okay, thank you so much.
And in an oxygen and nitrogen, it's not, right? It's so oxygen, nitrogen, yes, those are nucleophilic. Okay. All right, other questions about nucleophiles, electrophiles? And we'll be doing lots of examples of these. In fact, one of the first things we're going to do when we look at reactions is look and see if we can identify nucleophiles, electrophiles, so that we'll know where the reactive parts are. By 2 or 3 weeks from now, it should become second nature to just look for nucleophiles and electrophiles.
I have a quick question. On your third example, the oxygen is a nucleophile, but the carbon is not. And I know you explained that, but could you just explain that one more time?
On this one right here, there's a very mild dipole moment here. And so we've got a very mild dipole moment. And so if we think about a reactivity, you already have 4 things attached here. And if we know carbon only takes four bonds. So the problem with this one is for it to be able to accept those electrons. So if I added electrons to that carbon, what has to happen? Well, if I can only have 4 bonds, right, something has to leave. Well, if we look at this, what's going to leave? Well, the carbons aren't going to leave because those are really strong bonds. The hydrogen is not going to leave unless it's being pulled off by something. And the oxygen negative is not going to leave as a double oxygen negative, right, or a superoxide. And so what we have here is a position that is electron deficient, but doesn't have the ability really to accept electron density. The same thing could be seen when we look at, and again, let me pick a better color. So if we look at this protonated methanol, what's actually the electrophile here? Well, you would think that the oxygen with the positive is the electrophile, but it's not the electrophilic position. You actually have 3 possible, 2 particularly electrophiles. This is potentially electrophile, and that's potentially electrophile, right? Your hydrogens, not the oxygen, because the oxygen can't actually accept the electrons. What can happen is if I have a nucleophile, and what would be the most likely reaction would be, and since I used red there, let's go to blue, is that I'm actually going to react at the proton, right? The proton is going to be the fastest of these to react, having to do with its size, sterics, and its, right? And I'm going to end up with this species, okay? So here's a case where something that looks like my electrophile is not, that position is not my electrophile. It's electrophilic, but it's actually the hydrogen attached to that oxygen positive that's my electrophile.
Okay, thank you.
And similar, so the same reason that oxygen can't be electrophile is the same reason that we don't have an electrophilic reactive species here. We have an electron deficient species, but not an electrophile.
Okay, great, thank you.
All right, now let's look at mechanisms and arrow pushing. And one of the really great book things that I like about this book, again, I don't like the price, but I do like the fact that they break this down into mechanistic steps. So the mechanistic and arrows we're going to be looking at different types. And so if you think about our mechanisms as these types and sequence these together, you'll be able to learn any mechanism by actually thinking about nucleophile attack, a leaving group, proton transfer, rearrangement, right? All of our mechanisms are broken down into discrete subsets of these types of mechanisms. So nucleophilic attack is whenever we have a nucleophile attacking an electrophile. So here, nucleophile is attacking that electrophile, right? The bromine is my nucleophile. The carbocation is my electrophile, right? And it's just drawing a double-headed arrow. I signify a double-headed arrow by using the 2 electrons. So this means 2 electrons when I draw a double-headed arrow, right? I did not show my lone pairs, but if I wanted to, I could show all of my lone pairs around there. The negative implies that we have 2 electrons. Again, here, if we think about what's going on, let's label this one, right? So we have lone pairs, so this could be a nucleophile, right? We do have a proton, so we could potentially have a proton transfer, right? We have lone pairs here, so this could potentially be a nucleophile, right? But we also have an electrophilic position, right? And I'm going to draw this in a second, so let's look at electrophiles. So if we think about what two things that this could be is it could be a proton source, which we'll get to in a second, but this is not an acidic species, right? But it has the lone pair, right? So it's got the lone pair that's going to make it nucleophilic. So if we think about nucleophile, electrophile, right, that's going to attack here, and we get that lone, we get the pi bond to move up to make room for this new bond. Right? And we get the positive, right? So here we have a nucleophilic attack. So the first one, we have a nucleophilic attack with a negative species, right? Ending up with a neutral species. And the second one, we have a neutral lone pair reacting with a neutral electrophile. And again, we end up neutral, but we have a negative and a positive. The next category is loss of electrons, loss of leaving group. And here, when we look at a loss of the leaving group, it's just the bond breaking, electrons going back towards the leaving group. Right. To give us the stable leaving group when we're looking at potential leaving groups. The thing we're looking for leaving groups are stable leaving groups. We potentially could have a leaving group that doesn't break a bond. Doesn't break a bond between two carbons, but here, if we think about this carbonyl, that carbonyl could have, left, that bond could break, right? So we could also have species that disassociate like this to form the positive and negative, the Zwitterion form. Zwitterion just means positive and negative. And so we have loss of leaving group. So that's going to be one of the mechanistic steps that we can use. Proton transfer. So here again, we have our carbonyl, which is both electrophile and nucleophile in the same species. But in this case, what we're adding is this electrophile or acid, right? So proton transfer, the proton here is going to be our, and we can think about a proton transfer as a nucleophilic attack with a leaving group, but specifically in proton transfer is where we're looking for protons, right? And so therefore this proton transfer you can think of as a acid reaction. And proton transfers are the largest part of biological systems. If you look at any enzyme mechanism, there's probably going to be 2, 3 to several proton transfers in that mechanism. And correct that because that is incorrect. This should be neutral. Okay. So proton transfers. And then the last one that they're going to be looking at this point is going to be rearrangements. And there are several rearrangements we'll see before you finish organic 2, but the one we're going to be looking at for quite a while is going to be carbocation rearrangements. And what happens here, right, is notice that we are getting a change in our carbon skeleton. So what's happening, and I'm doing this because I learned it when I was in class, is put a little curly Q, that's just a sign for rearrangement. This book doesn't use it. You don't have to use it. But what's happening is I'm actually shifting, and I'll do this, right? I'm shifting this methyl. Now, why does that happen? Well, it has to do with our orbital. So when we think about a positive charge, right, I've got an empty p orbital, right? And then over here, and I'm just going to show one. I've got this sp3. So over here, I've got my p orbital, my sp3, and what's happening is I can get hyperconjugation. Which is the overlap of the sp3 with that carbocation, that empty p orbital. This hyperconjugation then leads to this, in this case, a methyl shift. It can also be an alkyl shift if it's not a methyl. In this case, it's a methyl, so it's a methyl shift. If it had been several carbons, you could think about it as a alkyl shift. Now, why does this happen? Well, it can happen because of the hyperconjugation. It will happen if I go from a lower stability to a higher stability carbocation. And if we look at the stability of carbocations, the stability increases as I increase the number of carbons adjacent to that carbocation that can hyperconjugate to it. So a methyl is going to be less stable than a primary, which is less stable than secondary, which is less stable than a tertiary. So in these rearrangements, if I can go from a lower, like a secondary to a tertiary carbocation, then that's going to be favored. And I can predict that potential shift because I went from a lower to a higher shift. And the stability has to do with the hyperconjugation. So carbocation rearrangements are plausible because of hyperconjugation, and the stability of carbocations is based on hyperconjugation. The other possible hydride shift, is a hydride shift. I gave it away there. So if we look at this one, this hydride, and notice I'm drawing it from the bond, which means the electrons go with it, right? That then results in my carbocation. If we look at what we've done, we've taken a secondary carbocation and gone to a tertiary carbocation. Right? So this is more stable. So one of the questions you're going to have with rearrangements is going to be whether a rearrangement will occur or will not occur. Okay, so let's look at a few of these. Let's try this. Let's take some time. You tell me if a methyl or a hydride shift would occur or would not occur based on the structure, and then show me what the products are. So let's take a little time, think through this one. Now, what's helpful on these is to go ahead and show in some hydrogens. All right, so you can see what's going on, and you just need to show the ones next to it. Okay, so in this first one, what would happen if we had shifted those electrons? So what would happen if I had shifted this electron? I mean, the proton, right? There are no methyls here. So if I shifted this proton, I would have ended up with that carbocation. So just what happens if? Okay. Is that changing the stability of the carbocation? Here I started with the secondary carbocation. Right? And what do I have now? I have a secondary carbocation. Right? Now, could this happen? Plausibly. Is it going to actually get a more stable species? No. So therefore, you know, there's really no reason for this to occur. Now, could it happen? Yes. Would I predict it to happen? No. Okay, is that somewhat clear? Since there's hyperconjugation, potentially I could have that hydrogen shift over. Okay. Right, the stability remains similar to the initial state, so therefore I don't really have any driving force. I have no delta G that's going to be advantageous here. So this reaction shouldn't be spontaneous. If we look at the next one, right, we have, yes, go ahead.
Real quick, can you explain again what hyperconjugation is?
Hyperconjugation is this overlap of this sp3 to a p orbital. So if there's a methyl, there's more electron density there, but that hyperconjugation between the sp3, you know, this sp3 and this p orbital is going to be in place whether there's a methyl here or not. So if this had been a hydrogen, there still would have been hyperconjugation, but with the methyl, there's more electron density and therefore more stability to that.
Okay, so it's the overlap of the sp3s.
sp3 with the empty p orbital.
Okay, thank you.
Yeah. So anytime we have that we have a carbocation, it's that the carbocation, that's why this is more stable, is now I have 3 possible hyperconjugations with the electron density of those carbons contributing to the stability of the carbocation here. Here I only have 2, right? Here I only have 1. And so this doesn't freak you out later. There, that should have a hydrogen on it. Right? Okay. All right, in this one, if you think about it, we could have 2 possibilities. So let's look. We've got the 1,2 methyl shift and the 1,2 hydride shift. Okay, so let's assume that we got a 1,2 methyl shift, right? And then let's assume that we got a 1,2 hydride shift, right? In the first case, did we change the stability? Well, we look here, right? We've got a secondary carbocation. Here we have a second carbocation. Would you predict a 1,2 methyl shift? No, I would not predict a 1,2 methyl shift because a 1,2 methyl shift would result in exactly the same species, right? Just carbon Bob versus carbon Mary. If we look at the second one, here we have a 1,2 hydride shift. What's happened? In the 1,2 hydride shift, I've gone from a secondary carbocation, right, to a tertiary carbocation. So in this case, right, I see that I have created a more stable species. So yes, I would predict a 1,2 hydride shift. In the last one, again, let's do both examples, right? So here's a 1,2 methyl shift, and here's a 1,2 hydride shift. So if we do the methyl shift, if we do the hydride shift, right, so we have the 1,2 methyl shift, 1,2 hydride shift. Here we're going from a secondary to a tertiary. And here, right, we're going from a secondary to a secondary. So I wouldn't predict the 1,2 hydride shift to occur, but I would predict that the 1,2 methyl shift would occur. And if we look at the 1,2 methyl shifts, usually you know a 1,2 methyl shift is occurring if you have a difference of 2, right? So here I have a quaternary carbon, 4 carbons attached to the same carbon next to a secondary. That will result in a tertiary. So therefore I know I have a 1,2 methyl shift is going to be likely. Hydride shifts don't have that same difference, but with hydride shifts, you still need to have a change to show that that is going to be a predicted product. Okay. Questions about rearrangements and hydride shifts, hydride and methyl shifts. Okay. We're going to focus on 1,2 methyl shifts. There are times when you'll see a species go through multiple 1,2s methyl shifts, but we're going to focus on just the straightforward 1,2 methyl shifts. You'll see a couple of advanced practice problems in the book. I don't believe I signed any, where you'll see multiple 1,2 hydride shifts to end up with the product. So you'll see 1, 2, 3 hydride shifts or methyl shifts to actually get a product. So, all right. So when we put these together, how do we combine our arrows? Right. So let's look at combining these. And first we'll just put our species out. So if we're looking at this reaction sequence, let's think about what we're doing here. And so in the first case, I have lone pair, that's going to be nucleophilic. I have an acid, right? So acid base. So if we think about this, nucleophile attacks the electrophilic position, which is the bromine, right? But in this case, what are we going to refer to this since I have a proton? What type of mechanistic step is occurring? Right, this is a proton transfer. So this reaction sequence starts with a proton transfer. Right? Then in the second step, right, if we think about what's happening, the water is leaving. And I should show this as equilibrium, right? And if the water is leaving by itself, then what mechanistic step is this second step? Okay, so this is loss of a leaving group. Right, and I can show the water out here by itself, right? And it could come back and attack back and do a nucleophilic attack, right? To go backwards. So loss of leaving group to get me forward. Now I have a carbocation. That carbocation, it looks like my structure has changed. That structure has changed, so that looks like a methyl shift. Right, so we have our methyl shift there. And again, notice here, I'm not using the squiggly arrow, but just the straight arrow. That's the way your book shows it. So we end up with this carbocation. Now I've gone from a secondary to a tertiary carbocation. Okay, so this next step is what type of process? So this is a rearrangement. And then I have my nucleophile, my bromide, right? Which came from my acid, right? That was the other species that was given off here. So then my nucleophile attacks my electrophile. So this last step is my nucleophilic attack. Okay. So this reaction process, right, is a proton transfer followed by a loss of leaving group, followed by a rearrangement, followed by a nucleophilic attack. This way we can get those together. Yes, that's rearrangement. And yes, that's leaving group. Nucleophilic attack. Okay. So we can start putting these together in these forms. So let's try another one. I'll give you a little bit of time on this one. Okay, with this species, draw your arrows. So if we look here, one of the ways to start is to think about what species you have. That's why it's important to look at nucleophiles, electrophiles. It's also important to bring in what are good leaving groups, right? That wasn't one of the things we identified, but it's important. And of course, when you're dealing with electrophiles, sometimes your electrophile is also an acid. So in this case, this is an acid, HBr, but the hydrogen is my proton or electrophile species. My double bond over here, we know pi bonds, right, can be nucleophiles. So the first step here is nucleophile attacking that proton, right, and kicking off the bromine. Now, since this is a proton, I can call this a proton transfer. If it had not been a proton, then this would have been a nucleophilic attack. Okay, that forms this carbocation. Again, now, what is the carbocation? Well, that's my electrophile. What is the bromine now? My bromine has switched from a leaving group to a nucleophile. What is the nucleophile going to do? The nucleophile is going to attack the electrophile. So this reaction of an alkene with hydrogen bromide is going to be a proton transfer, right, to form the more stable carbocation, followed by nucleophilic attack. And I noticed that we haven't covered this reaction yet, but because you know what the nucleophile and the electrophilic species is, you should be able to predict what's going to happen. So let's look at another one. Again, a reaction we haven't learned. But let's see if we can predict what's going to happen and what the mechanism is going to be. Okay. So if we look at our first species here, right, we've got an oxygen negative. That oxygen negative is going to be my nucleophile. If we look at our second species, I've got a bond dipole here, right? We got lone pairs on the bromine, but the bromine, those lone pairs aren't available. But that partial positive and partial negative means that this methyl group is my electrophile. And would the bromine be stable once it's left? Is a bromine negative a stable species? Halide negatives are very stable, right? So I can say that this is going to be a good leaving group. So if we look at nucleophiles, what do nucleophiles do? Nucleophiles attack electrophiles. What do leaving groups do? Leaving groups leave. And I can predict, based on nucleophiles and electrophiles, that this is my product. Right? I've turned this alcohol into an ether. Okay. Questions? And this one, if we get back to our, let's name these things, this is a nucleophilic attack. Now notice that nucleophilic attacks often also have loss of leaving group embedded in them. They all occur at one time. So we call loss of leaving group if the loss of leaving a group occurs by itself, right? So if we look back at the loss of leaving group up here, the water left, right, without something coming in and forcing it off, versus this nucleophilic attack here, right, where that nucleophile is coming in and the other one's all leaving in one process.
I have a quick question on that.
Mm-hmm.
Is the bromine the leaving group in this case because the oxygen is more electronegative, or like why doesn't the same thing happen to the CH3O? Like the other way
Oh,
around?
going backwards?
Yeah.
Right. So then it would be, is this reaction going to be thermodynamically stable going forward or backwards? And so then you would compare, the easiest thing you would compare here is the stability of this to the stability of that. So could this come in and attack that carbon and kick off this? Yes, that is plausible, right? So then it determines whether this is going forward or backwards really is going to be delta G, right? What's my lowest energy species? And so if we think about our bromide to our oxygen negative, which one's more stable? Well, since this is a halide, right? Halides have a higher electronegativity and they are a more stable negative than the lower electronegativity oxygen is, right? So halide leaving groups versus oxygen and nitrogen leaving groups, right? So therefore, from just the nature of these two elements and where they are in the periodic table, I can say that this is going to be more stable than that, right? And so therefore, this reaction is going to proceed in the forward direction much more than it would in the reverse direction.
Okay, that makes sense.
Okay. Now, if I put the bromine and ether, right? The bromine is a nucleophile and the ether is a potential electrophile. But the bromine, the reaction, if that happened to occur, like they just bumped into each other, it would quickly reverse because the forward, it's not spontaneous. The delta G is in the wrong direction. Okay. So we're starting to put these things together. So what this chapter really does well, and right now we're actually done with this chapter. So let's kind of wrap it up. So is that we're going to be coming back to this chapter over and over and over again as we go through the next chapter. So at this point, with chapter 1 through 6, what you have is really the basis for the reactions that we're going to be looking at moving forward, right? So if we look at all the reactions, we're going to be coming back to nucleophile attacks electrophile, nucleophilic attacks, proton transfers, loss of leaving group, rearrangements. All of our reactions are going to be made of that. Our reactions are going to proceed forward if the delta G is negative, right? We're going to have stereoselective reactions based off the previous chapter and based on the hybridization that we saw in chapter 1, right? So as we put this all together, that's what we're going to see. So today, I've already foreshadowed several reactions you're going to see over the next several weeks, right? So this one right here, we're going to see this reactions over the next several weeks. The alkene, we're going to see that when we get to alkene reactions. And then this one, we're going to see when we get to ethers and epoxides, okay? The lectures, you can see those, the link for the lecture is on Canvas. So if you go to the modules, so go to modules, and then everything related to chapter 6 is under chapter 6 module, and you'll see the notes up there, and you'll see the lecture videos up there. I do post the lecture videos on YouTube just because it's easier for me, and I don't mind them being available for the public. And just go to the modules on the Canvas page. That's where I put everything. Okay. With that, it is now 10:20, so we'll go ahead and call it a day unless there's any last minute questions.